Hello, my name is Prioleau, and I am an undergraduate research assistant, and I will be presenting for our research of sentiment classification of code switch text using pre-trained multilingual embeddings and segmentation. And this is a part of the Effective Biometrics Lab at Howard University. The mission of the Effective Biometrics Lab is to give voices to individuals or communities that feel marginalized through AI systems that leverage physiological, or behavioral characteristics for identity or emotion recognition. Our research tries to address and answer questions like who is that, what do they feel, how are they going to react or behave, and what can I build or develop to positively impact human feelings. The authors of this paper include myself, Howard Prioleau, and then it also includes Dr. Aryal and Dr. Washington. And then now is the presentation of the research. Sentiment analysis. In the modern world, humans produce vast amounts of data, and most of that data is in text. The task is given the user-generated text, classify sentiment polarity, usually positive versus negative, or three class of positive, neutral, and negative. The text goes into the model, and then the model produces a sentiment label of either positive, negative, or also three class of neutral as well. Sentiment analysis and classification has proven to produce outstanding results across multiple domains. Bidirectional encoders representations from transformers, BERT, and related variants have provided state-of-the-art embeddings for numerous natural language processing tasks, including sentiment classification. However, these works were initially limited to English. In a world where 7,000 plus languages are spoken and half of them are written, sentiment analysis needed to be extended to branch out to other languages. But other languages might not have the resources that English does, or the availability on the internet or through data gathering sources. While many multilingual models were proposed, currently XLM Roberta has provided state-of-the-art embeddings for over 100 languages. However, multilingual models, while working on monolingual sentences across many languages, do not work well with mixed language texts. What is code switching? Linguistic code switching is the current use of two or more languages or dialects in a conversation. An example of this between Spanish, ES, and English, EN, is Sol, happy birthday, que tengas un lindo día y que cumplas muchísimos más. And so with this, there's two languages being used in this happy birthday. And when translated to pure English, it means happy birthday, have a nice day, and many more to come. And why is code switching important? Sociolinguistic research suggests that 50% of the world is bilingual, but internet text content is dominated by few languages. Non-native speakers of popular languages are routinely observed using code switching in online social environments. For example, like mixing Hindi and English on Twitter, same as Spanish and English as well on Twitter as well. As the internet accessibility and technology advances, the intermixing of languages is also likely to expand, and with that will lead to a lot more mixes, maybe even between languages that aren't centered around English as well. Research problems and questions. While sentiment analysis has proliferated over the past decade, with most of the research in the field being focused on monolingual textual data, code switch data makes sentiment analysis a more complex task since two source languages unification creates a tertiary low resource language. And sentiment analysis, literature, and data on code switch text is increasing, but still limited. Work is designed and implemented for specific language pairs only. Related works and current techniques. Currently, bilingual models and embeddings work well, but scales linearly with the number of distinct language pairs. Custom neural architectures proposed custom architectures around code switching design around the topology and the features of specific language pairs. Designs are inspired, thus limited by the topology of the specific language pair being studied. Essentially, that if we were to focus on an architecture that works on Spanish English, it will most likely not transfer as well to another pair such as Hindu English or something of the nature. And our proposed algorithm, we propose a multi-step natural language processing algorithm utilizing the text. First is the detect of code switching and mixed text. Next is language segmentation, which would be where we split up the sentence or the text into each of the prospective languages. So like for a Spanish English text, we would split it. We would have one for the same sentence, we would split all the words that are Spanish into one, all the words that are English into another. And then we would conduct semantic similarity around those segments with a bag of language specific positive versus negative lexicons. And so what we would do, we would run semantic similarity and score the comparison between English and then the English positive words and then the English negative words, and we would see which one was our text closer to through some semantic similarity scores. And with that, we would also do that for the other language of Spanish. And then through that, whichever value was higher between positive versus negative for each side, well, through the four comparisons, is what would be predicted as positive or negative for the entire text. Yeah. We would compare the numbers of positive and negative sentiments, aggregate, and threshold to classify. And to the right is our proposed algorithm and like data flow model. The current baseline in the field of the approaches we chose as our baseline. Oh, okay. We chose. Oh, I'm blanking. I believe it was GERNet as our baseline comparison and is the current state of the art for the specific dataset task pair and has shown improved performance when compared to over 10 other approaches using an expert design neural architecture. This is what it was able to score on the same task that we are trying to implement. and they were able to score a 63% accuracy, 62.4% macro F1, and a 63.4 precision, and a 61.8 recall. And that was the best performer between the two GERNet models. The data sets that we primarily used in this research was the Spanish English code switching data set. This data set is comprised of tweets that contain both Spanish and English. And then for our word level sentiment lexicon data set, this was the data set that provided our ground truths of negative words and positive words per language. They also have a lot more languages, but we only utilize the ones for Spanish and English. Our methodology. First would be our data pre-processing. We would convert the text to lowercase and remove all punctuations, white spaces, and stuff of that nature. And then we would also remove sensitive identifying information such as email addresses, URLs. And further than that, we would also remove social media text such as like hashtags or like ats or like usernames and stuff of that sort, to be able to get only the text to analyze instead of having the stuff that would fuzzy up the data. And then our focus was the two pre-trained multilingual models to extract sentence level embeddings, and we use XLM Roberta and Universal Sentence Encoder from Google. And our hypothesis was that sentence embeddings of segments that are negative will be closer to a set of negative lexicons versus positive lexicons of the same language. Our methodology continued. Code switching identification algorithm. We utilized the native Bayes classifier on our Spanish English data set to detect points where code switching might occur. And so with that, for our native Bayes classifier, I would like to speak a little bit more on that. So like, for example, for our Spanish to English example, our Spanish English language pair example, we would try to predict where the language would switch from the English to Spanish and then Spanish to English. And we use that to be able to separate and segment the languages. Then for our sentiment analysis algorithm, when the two languages were segmented into consonant languages and then the embeddings were extracted once they were separated. And then the segments were compared to the language-specific sets of negative and positive embeddings, and the total score of the similarity between each language was calculated. Whichever score is greater will be the prediction. And our results. So as you can see, we were able to outperform the GERNet baseline models pretty well with both of our proposed multilingual models that we use. And so with Usenet not being as accurate as our excellent Roberta base, it was still able to outscore with getting a 71.9% accuracy, 71.7 macro F1, a 74.5 precision, and a 73.4 recall. But for our excellent Roberta based model, it was able to perform the best and outscore GearNet by over, I believe, 11%, with accuracy being at 74.5%, macro F1 at a 74%, precision at 74.2, while lower than Usenet, still very close and similar, and then recall being higher at 73.8%. And so with that, excellent Roberta base did have the higher accuracy, but it was outperformed by Usenet in false positives, in that Excel Roberta base had 201 false positives in comparison to Usenet having only 77 false positives. And then it was similar, but vice versa, where it was false negatives were a lot more for the Usenet model, and then for the Roberta model, false positives was a lot lower. Limitations, performance improvement. While we were able to get into 74 into the 70s of accuracy, it leaves much more to be desired in what is possible, and to be able to use these models in a real world setting and analyzing code switched text, specifically Spanish and English. The proposed design is language agnostic. And so while we believe that our design probably only works for Spanish and English, we haven't been able to test it. I mean, the vice versa. Work is not comparable to Indic language sets and other language pairs currently. And with that being said, is that we won't be able to apply this onto other language pairs or other language sets that are currently available. Since that French, Tamil, Nepali, English, Hopi, Tiwa, and much more are language pairs that are currently just not available, or due to the lackings of the code switching data set. And then also with the removing of emoticons and other data and cleansing also means that we potentially lost some information when it comes to sentiment analysis, due to emoticons and like hashtags maybe also being a vital part in one person's sentiment towards something. And so like, let's say if somebody uses like a laughing emoji or a smiling face, that usually means that it is positive. But let's say if they're using that crying emoji or a sad face, that would usually mean something is negative. And so preferably we would like to be able to use models that are able to read emoticons, and while they still aren't as like at like the level of like Roberta models, they are still some that are starting to gain popularity that might be able to even improve our performance even more, being able to keep emoticons and other data into the data set. Further limitations, dependence on large-scale multilingual models. And so with that, since this is a low resource language, the large-scale multilingual models could potentially exacerbate the issues due to the fact that the data sets are small and whatnot. And so that we would still need human expertise to create positive and negative word sets for the language of choice. And this is because there's no trusted automated process or models that would be able to do this on its own. And so when it comes to data sets, this is also why it's so limited, in that you would need humans to hand label all the data points to be able to get an accurate reading. And even then, you might even have some like false positives, false negatives, or wrong labels in general. And to avoid that, you would need even more people to look at the data to confirm that people are labeling it right. And then our approach is rudimentary, and better approaches will be available once data is available. Future work is potentially to extend to other language pairs available, such as I know that there's Hindu English, there's Tamil English, Tulu English, and then there's also some African languages to English as well that is currently a new data set that's being adopted into the code switching data set base. And then also the creation of other data sets and language pairs. Due to a lot of the current data sets being tied to English, we would like to try to make our own data sets that aren't particularly focused around English. So like, let's say if we were to try to do a language pair of Latin as previously as previously stated, between like Latin and Irish and stuff along those lines, or like some French and African languages or stuff like where that English is not the base pair, and so that we're able to fully broaden the spectrum of code switch data sets. Also, unsupervised slash self-supervised algorithms where annotation may not be required. And so what that is just gathering code switch data sets and then having them cluster based off a similarity between the text that, and then go from there. And so we wouldn't have as much as a problem with having to label all the data sets if we go with more of an unsupervised approach to the data sets or even future data sets. And in conclusion, the results show that our approach significantly surpasses the baseline performance of GERNet by 11.2% accuracy and 11.6% for the F1 score. Theoretically, the proposed approach may apply to a number of downstream classification tasks and applications that involve code switch textual data. However, larger and more comprehensive data sets may enable more complex and better performing approaches for language agnostic sentiment analysis of code switch text. Yeah. And that is all for my presentation.